Yeah, go for it.
All right, well, thank you all for coming. So my name is Caleb Christensen. I'm a PhD candidate at UC San Diego. I'm in the nanoengineering department, but my research is on soft robotics. So soft robotics are just robots that are made out of rubber instead of rigid materials like metal or plastic. So one reason for that is that one of the challenges that I have with traditional robotics is safety. So for example, we have Terminator. So a lot of traditional robots are made out of metal, they move very quickly. So industrial robots that are working in factories are often put into cages to keep the robots from smearing people across the wall. So we don't want that. And so if you want to talk about home healthcare robot, so somebody that can take care of grandma when she's at home alone, you don't want Terminator to take care of her. Maybe you want something more like Baymax from Big Hero 6, or something a little bit more soft and cuddly, a little bit more compliance. That way, if she accidentally bumps into grandma a little too hard, it's not going to hurt her. Okay? So that's why one of the motivations for pursuing soft robotics is that we want to think about robots in a safer way. And then another reason is for adaptability. So people, animals, we're all really great at moving through robust and different environments. So we can jump over things, we can run through things. However, robotics still has ways to go with that. So this is brand new, 3 years old, but this was the state of the most advanced robots in the world as of 3 years ago. This is from the Graphical Robotics Challenge, in which the best and brightest robotics groups in the world invested millions of dollars to get their robots to perform what would seem to be fairly simple tasks, such as crossing a road. But what DARPA didn't tell the teams ahead of time, though, was that the road would be made out of sand. And so these very expensive, very robust robots couldn't walk over sand. So one of the advantages of soft robotics is that they can conform to a variety of different environments. And so, for example, instead of having to program a robot to walk over sand specifically, or make feet that can adapt to many different environments, if you just use soft robotics, it can do a lot of that inherently because of their compliance. So I'm going to show a few videos of soft robots. So the one on the left is from a group at Harvard. Actually, these are both from a group at Harvard. The one on the right is from my professor when he was there doing his postdoc. So these are some soft quadruped robots that are pneumatically actuated. And so the way that these work is that they're made out of a rubbery material, and each of these legs have chambers in them that you can inflate pneumatically. And then as you inflate them, it'll bend, and you can control that bending in a sequence to get it to move through the environment that it's in. And the one on the right, you can see that it can move through a variety of different terrains like snow, sand. It's walking over a fire right now. And so they're a lot more robust. The challenge with these is that they're a little bit slow. If you notice, the video on the right is sped up 8x. And so one of the challenges with pneumatically actuated robots is that they're inherently slow, because it takes time to inflate and deflate each of those sections. Another challenge with pneumatically actuated soft robots is that you need an air compressor of some sort in order to generate that pressure to pump up each of the sections. And so my research focuses on using electricity to deform rubbery materials instead of using pneumatics. That we can get something that's a little bit more faster, more effective, a lot more efficient. Okay. So using electricity to deform materials, this actually, we'll get to this one. So it's made out of rubber, and you can drive over it with your car, and it'll still keep moving. So goes up to the car, slowly, carefully, safely, then drive over it, and it'll walk away. It's not always possible to do that with plastic or some metal-based robots, but that's one thing that you can do with rubbery robots. In fact, we still have that robot in our lab today, even though it's over 4 years old. So using electricity to deform materials, so this is going back to high school or undergrad physics, a capacitor. So a capacitor is two conductive plates, one on the bottom, one on the top, and then some sort of non-conductive material in between. And then you can apply a voltage to either side of the conductive plates, which will charge up the dielectric, and you can store energy on the capacitor. What's interesting is that most capacitors are made out of rigid materials, either some sort of polymer But if you make it out of a flexible material and you use a high enough voltage, you can actually get this to move. So it looks a little bit like this. So here we have a conductive material on top that's compliant, conductive material on the bottom, and then a rubbery dielectric layer. And then as you apply a voltage, the charges build up on either of the surfaces. So you have positive charges on top, negative charges on the bottom. They want to get close to each other. So you have this compression and thickness. But then also all the buildup of light charges, they want to get away from each other. So you have this expansion in area. So it gets thinner and more spread out because of those two effects. And this is the only equation I have on here, but since I'm a grad student, I have some equation on here. So this is the pressure as a function of voltage. So the pressure that you can generate with these electrostatic forces goes as the voltage squared over the thickness. So if you want to get a really big voltage, really big pressure, you can either use a lot of voltage or you can use a really, really thin layer. These other two, the epsilon R is the permittivity of the material, which we have a little bit of control over depending on which material we use, but it's anywhere from like 1 to 4 or 5. And then this epsilon naught is the permittivity of free space, which we can't really control. Okay. So the parameters that we have are how much voltage we use or the thickness of the material. So if we want to make an actuator that performs a lot like natural muscles, one way of looking at it qualitatively is through these different metrics, and it's a little bit fuzzy on this screen, but I'll read them out to you. So this first column is different types of actuators. Then we have strain, actuation pressure, density, efficiency, and speed. And then a black circle means that it's good, a white circle means that it's bad. Okay? So the top row is natural muscle. And so we say that it's good in all these different categories. Other types of actuators have some sort of trade-offs. So like this one says electromagnetic. So it's good with strain and actuation pressure, oh, that's awesome. Getting into focus, or my eyes are getting better. So electromagnetics, density. So they're very heavy for what they are. And then speed, they're very efficient at high speed, but they're not very efficient at low speeds. So that's what that's saying. Whereas if compared to DEAs, dielectric elastomer actuators, they're similar to natural muscles across all these different categories. Yes?
Did any of these surpass human muscles in any category?
These, the dielectric elastomers or the other ones?
Yeah.
Yeah, I mean, there's also, if you think of electromagnetic motor, you can generate a lot more torque or force than a natural muscle.
So is that a soft muscle?
No. So these are a range of different types of muscles. So in terms of soft muscles that can outperform human muscles.
In any category?
In any category. That's a good question. Let me show you one more picture while I kind of stew on it, and I'll get back to you, if that's okay?
Sure.
Okay. Here's a graphical representation of this plot, of this data. So this is a different way of presenting some of this data. So on the y-axis we have strain, so how much it can move, and then actuation pressure divided by density, so the amount of force that can generate divided by the weight or the density of the material. And so up here we have, on the x-axis we have piezoelectric and magnetostrictive actuators. You can get really high pressures, but at very small strains. So piezos, you know that they can generate a lot of pressure, but they don't move very much at all. Or on the y-axis, if you want something that can generate a lot of strain, magnetic and electrostatic actuators, they can generate a lot of strain, but they're very heavy. So they don't compare as well to natural muscles in that respect. So we have in the center, the Goldilocks, we have dielectric elastomers. These different colored circles are different types of elastomers that you could use for DEAs. And then in the center here is where natural muscle would fall in. And so to answer your question, so if you look at acrylic elastomers, at least according to these two metrics, they outperform natural muscle. Yeah, if you guys have any questions as we go through this, we can stop. We'll give me a chance to get a drink of water.
Do you have any samples of any of these materials with you today?
You know, I do not, and that's a mistake on my part. But I will try to mime out what they look and feel like, and I've got lots of videos, so I hope that will give you kind of a sense of how they move and how you can play with them. They're also very inexpensive. You can buy them on Amazon, the raw materials, and I think in 2 slides I have a list of the things that you need to buy.
Oh, cool.
And it's very inexpensive. So there's one other interesting thing that I want to talk about here about dBAs is that they're also, so if you go back to this equation, the pressure is equal to the voltage divided by the thickness. As you increase the voltage, you're compressing the material, so you're also decreasing the thickness. And so if you keep the voltage constant, your thickness is going to keep going down as you're applying that voltage. So you're getting this kind of feedback loop. So you're applying the same voltage but across a thinner and then a thinner elastomer, so you're getting more and more pressure. So then if you use a high enough voltage, you're actually going to squish the elastomer until it breaks down. And so we can see that here on this plot. So I'd like you to ignore the dashed line for a moment and just focus on the solid blue line. So this is kind of a weird plot, but in my field, this is how they describe this. So on the y-axis is the voltage. So you can think about this as kind of your x-axis. So as you increase the voltage, on the x-axis is the strain, or how much it's moving. And so as you increase the voltage, it's straining a little bit more and a little bit more and a little bit more. And then at some critical voltage, it's just going to get a lot bigger for the same amount of voltage. So they call this snap through, and it's based on that positive feedback loop. Okay? So you go up here, so as you're increasing, so you go from, say 1,000 volts to 2,000 volts, up to 5,000 volts. And at this point, so you're just moving a little bit at a time, and then at some critical voltage, it's just going to move a lot, or you're going to be compressing your film so much that it's going to break the film because you're applying too much pressure. And that's what this red line is indicating, is the breakdown strength of the material. So for each material, it has a certain dielectric breakdown strength. So at a certain voltage, at a certain thickness, if you use a high enough voltage, it's going to just arc through the material, it's going to spark through it. And so that's what this red line is indicating. So as you increase the voltage, eventually it's going to squish and you're going to break down and destroy your actuator. What somebody figured out back 18 years ago is that if you take this rubbery material and you stretch it out ahead of time, so the way that you make these actuators is that you take the rubber, you paint your electrodes on them, and then you apply a voltage and you can watch it move. And you can get about 30% strain if you just do it like that. But because you get 30% strain before you hit this breakdown. But if you actually stretch the rubber out ahead of time, and then paint your electrodes on, and then actuate it, you can get 100% strain, or even 200% strain. Some people have even reported 1,700% strain. And what you're doing is you're actually aligning the polymer chains. So if you think about the elastomer as like a bowl of spaghetti, where you have all these different noodles that are going all different directions, when you stretch it out, you're actually aligning the chains, and that keeps it from being able to break down as easily. So there's fewer conductive paths through the thickness of the material because you're holding them all sideways, which is kind of interesting.
If you use the material several times before hitting that red mark, is there ever a point where it starts to wear down, where you need to increase the voltage to get to that same result over time?
Increase the voltage?
So I guess, because you're actuating
Right.
it with voltage, right? So does it wear down essentially before, like, if you use it like 1,000 or 1,000,000 times, right? But you're not hitting the breakdown point.
Right.
Will you need more voltage in the future to move it the same amount because of the, like, I guess, a breakdown of the material or something like that?
So there's a few effects when you actuate them a lot of times. One is going to be that you might not break down a very big hole through the material, but you might do like a small hole. And so you'll see if you watch like the amount of current. So if you apply a fixed voltage and you watch the amount of current, you'll see several small short spikes where you'll have like small breakdown through the material, but sometimes it's not catastrophic. You can keep using the material. But then as long as you keep using the same voltage, you should still be able to get the same amount of actuation as long as you have enough power to generate enough current. So what you're going to be losing out on is the current that could go through the material. So ideally there's no current going through the material, but as you break down, you're going to be getting more and more current that goes through the material. So you can use the same voltage, but you would need more power to go through it.
So,
Yeah.
let's say you have a hand, there's nothing to open and close. So you're saying that would not deteriorate as long as you didn't stress it.
I'm sure it would deteriorate because nothing lasts for forever. There's of entropy and all of that. I think what's going to, in my experience, what happens first is that it's going to break down first. So you'll achieve some sort of dielectric breakdown.
So it'll break down regardless of it's on stress or not, at a stress level or not. Like it's not under stress, it's opening and closing like it normally would. I don't call this stress, it maybe could be. But it will break down because that's just the way things are, right? I mean, human would break down eventually too, but at the same time, it can also get stronger.
Right. Yeah. So because you're straining these polymer chains, eventually those bonds are going to break, and then eventually the whole thing would just.
So to answer your question then, yes, those polymer chains will break down normally.
And then another interesting thing is that just like blowing up a balloon, so so if you blow up a balloon, sometimes you'll stretch it out first ahead of time. That's called a strain softening. Anyways, if you stretch it out ahead of time, it actually makes it easier to blow up. And so when you actuate these, you can kind of see the same thing. The first few times you actuate them, you might get more of an effect. You'll get less of an effect until they soften up, and then you can actually get more of an effect. And then that's also similar to this right here. If you think about when you're blowing up a balloon, it's really hard to blow up at the very beginning, and then it gets really easy, and then towards the end it gets really hard again. That's very similar to what's going on here. So this is voltage, right? So this is the amount of force that you're having to apply in a sense. So it's really hard to apply force at the beginning, and then it gets really easy, and then if you can go past this breakdown, then it gets harder again as it gets stiffer. So this plot, the dashed line, is showing that if you stretch it ahead of time, you can actually avoid this whole scenario where you get to a peak and then it just breaks down and crashes. If you stretch it out ahead of time, you actually can do where you apply this voltage up to this point, and then it'll just quickly increase, and then you have to apply more voltage before you get to the breakdown. So it's a lot more stable that way. I think what I have left are, so next is advantages and disadvantages. So the advantages are that you can get high strains out of these materials. There's a very high energy density, on the order of joules per gram. They're highly efficient in terms of 90% conversion efficiency between the amount of power that you input and the amount of work that you get out of them. Fast actuation, you can actually make speakers out of these. People have gone up to 20, 40 kilohertz, so you can actually make speakers out of these. They're inexpensive, so the parts that I'm using, it's on the order of about $1 per foot or so for the elastomer material, but you can also get it cheaper too. And then the conductive is usually just like a paste that's very inexpensive, very easy to make. Disadvantages is that you need high voltages, usually kilovolts, anywhere from 1 to 10,000 volts in order to get enough pressure to get these things to move. Low blocking force, so if you want something that can actually withstand a lot of force, this isn't the actuator for you. If you want something that can move a lot, it might be good, but it's not good at moving and then also holding its shape. But you could also design like a ratcheting system that could hold that shape for you. Yeah.
Sorry, because it's also a capacitor, and so if you're running this through like a range of frequencies, does it also produce a high pass frequency effect, high pass filtering effect on the material?
It is. Let's see. How so?
Well, I guess because like the capacitance would block out any like lower frequency ranges, assuming, or I guess constant.
That's interesting. I'm sure I haven't quite looked at that. I'm not sure yet.
No.
Yeah. But
No worries, I was just curious.
So a lot of times when I'm running these, I'm operating in the low frequency range. What I call low frequency is about 0.1 to 1 hertz.
Oh.
So I'm not sure. I need to look into that one. In terms of the materials that you need to make these, so the dielectric elastomers usually come in two different flavors. One is either an acrylic-based elastomer, the other one is a silicone-based elastomer. You can get the acrylic, you can get both of them on Amazon. You can get everything on Amazon. But the acrylic one that most people use is a tape from 3M. It's called VHB for very high bond. It's used for sticking aircraft parts together, but people back in 2000 at SRA International found that they were just trying a bunch of different materials, and they found that this tape works really well for these actuators. So they were just trying a bunch of different things in their lab, and this worked. So a lot of people that make these actuators use this tape. And it's convenient because it comes on a roll. And so if you want to just prototype something very quickly, you can just buy a roll of it, put some electrodes on it, and then you're good to go. It also has a very high permittivity, relative permittivity. So the very first number in that equation was the relative permittivity. So it has something on the order of 4.7 relative permittivity, whereas silicone is something closer to 2. So with an acrylic-based elastomer like this VHB, you can get about twice the amount of pressure that you can versus a silicone elastomer. But a silicone elastomer can operate at higher frequencies, and so there's some trade-offs between the two. Other differences between the two materials is that VHB comes in mostly two different thicknesses, either 1 millimeter or 0.5 millimeter. Whereas with silicone, it's a lot easier. It usually comes as a liquid, two-part liquid, that you can spin coat to control the thickness of the material that you want to use. So you have a little bit more flexibility with silicone, but you have a lot more ease of fabrication with acrylic. For electrodes, you can use a variety of different things as long as it's conductive and you can control where the electrode is, and it has to be compliant. So you want something that can flex with your actuator. So people don't usually use metal electrodes unless you do something clever with the shape so that way it can bend and stretch. People usually use graphite or carbon grease, conductive glue dust, or conductive fluids. The most common one is this conductive grease. So it's basically a silicone oil with carbon particles in it. I think actually now you can get that on Amazon. It used to just be on like McMaster or something, but again, you can find everything on Amazon or wherever you want. So these are the two materials that that a lot of the DEAs are made from. These are a few of the different configurations of DEAs. So you can put them in a variety of different shapes and designs depending on what kind of actuation you want to get out of them. So for example, an extender, so you have several of them in a stack. And then as you apply the voltage, it's going to compress the thickness and expand in area, so we'll just go out that way. Bimorph and unimorph, you put one or two of these back to back, and as you apply the voltage, it's going to bend one way or the other way. For bimorph, for unimorph, you have one actuator stuck to something that can't extend. And so as you actuate the DEA, it's going to get longer, but the inextensible layer can't, so it bends towards the inextensible layer. These bow ties are where you have a rigid frame on the top and the bottom, and then you have some tension between the two. And then as you apply the voltage, the black part's going to expand in area, so you go from a short to longer. Okay. And there's a few other designs as well, but these are most of what we'll be talking about today. So I'm going to show you some examples of what other groups have been doing with their actuators, and then I'll show a few videos of the stuff that we're doing with ours. So the first one is a group from EPFL. They have this gripper that they've made. So this is several different patterns of DEAs, and then as you apply the voltage, you can get this curling that will reach up. And then they put a few of these together into this hand, so we can grab onto objects. They were actually using this, or the idea for this was to be deployed out in space to pick up debris, but it hasn't actually been deployed yet. That was the design idea. This next one is really interesting, I think, as it plays. So we have two petals of DEAs, and then as it gets to the egg, you actuate the DEAs that go, and they'll go from this curved out shape to a curved in shape to grab onto the egg. That's part of it. The other part is electroadhesion. So since we're using high voltages, we can use electrostatic adhesion as well. That's interesting. So they have these interdigitated pads at the tip, and so as they apply voltage at the tip of the actuator, it'll electrostatically attract whatever it's touching. So using that to pick up different objects. And then this last one is Rupert, the rolling robot, and I believe they ran it for, I think it was the length of a marathon. It went around in a circle enough times to count for 26.2 miles, or something similar. And the way that it works is that you have a disk of DEAs, and you have 3 different slices of DEAs, and then they have a rod through the center, and then as you actuate each of the segments of the DEA, you will cause the rod to bend in different directions, which will cause the whole thing to roll as it rolls along the track.
So it's not getting external power from the track?
It is, yeah. So there's most likely one's a high volt positive rail and one's a ground rail on the track.
Okay. And what did that demonstrate? Just a different way of making an electric motor?
Yeah. But where the actuator is, the actuator of it is soft. This is also kind of interesting. It's a Caterpillar, sort of, robot from the University of Auckland. Kind of cute. They 3D printed the head. And then they have these 6 different DEA segments. And then again, just like that last one, they have 2 rails. There's a positive rail and then a ground rail on the outside that it's driving along. And then it's using the soft material to actually determine or to control which of the segments are being actuated at a time. And so you'll see these the traces that are kind of zigzag traces in between each of the actuators. And so as one of the actuators expands, it compresses the zigzag traces so that way it's conductive. So it goes from an open circuit to a closed circuit. And so as one expands, it completes a circuit, so then it passes the charge off to the next one, and the next one, and so on. So it's kind of a clever way of, without having any onboard electronics on the robot itself, you just have a DC rail, and then it controls it using the properties of the materials. Group from Harvard made these really nice DEAs where they have carbon nanotubes on a very thin acrylic elastomer DE. And so they have 4 different quadrants in this example, and then as they apply voltage between each of the quadrants, they can get each of those edges to curl up individually. And what was neat about this paper is that, so they're using the same type of elastomer as the VHB, the one that you can buy on a roll, except for they made their own liquid version of it so they could control how thick it was. So they can have a very thin layer of a really high performing DEA. And then they also made it into another Caterpillar, because I guess, internal, it's a little bit better. It actually moves pretty quickly. It's kind of hard to see. Then they put it into kind of this quadruped type shape and actuate each of the legs, get it to crawl out. They also put it onto a fish, a swimming type robot. So they have a 3D printed body with all the electronics inside this watertight container, fully watertight. And then they have a fin that's made out of the same type of material. And then as they actuate it side to side, they can get it to swim through the water. Then this is from a conference back in March that I went to. It was really cool. Because you can actually reach in and touch the flipper. I mean, there's a few thousand volts. It's very low current, very low power, so it's safe to touch. But like I said, most of these generate very low forces, but the way that they've made theirs, because they're really thin layers and they've stacked many layers together, you can actually get more force if you have more layers stuck together. So it's really fun to actually go out there and touch these. And they have pretty good performance with them. 2 other swimming robots I want to show you guys. This one is a 9-meter long blimp made in Germany, Blimp. So they have these giant DEA panels on the side, and then at the tail of the robot, and then as they actuate it in sequence, they can get it to swim through the air, which is pretty neat. So who doesn't want a 9-meter long fish robot? And then the next two are back again from the group at EPFL, where they made a soft swimming robot like a fish, and then also another one like a jellyfish. This was their work 2 years ago, and then just this summer they released this update where they have much better control over the way that it's made. It can swim a lot more elegantly. Jellyfish, they're still working on the jellyfish. Jellyfish are really hard. That's actually what I'm working on right now. I don't have any videos of my jellyfish because it's really hard to make a jellyfish swim using soft materials, at least in my experience. And there's two.
Well, if jellyfishes really swim, they don't have any problems, though.
No, they don't. They've got it figured out. They haven't been working on it for a lot longer than I have, though.
So you need
Yeah, right? So I have some catching up to do, that's for sure. How are we doing on time? There's a clock. Okay, cool. So we're just about to the my part, but we have 2 more slides. Another one, this is another group from Asia. They made this manta ray swimming robot where they have, so they took the elastomer and they pre-stretched it to get that better actuation, and then they poured silicone mold on top of it to form the body. And then after the mold cured, after the body cured, then they released the pre-stretch of the DE, which caused it to bend a little bit. And then as you actuate it, what you're doing is you're allowing the material to relax, so it goes from a bent to a relaxed state. And they could get it to move fairly quickly, get it to swim through the water. And they also made this completely untethered. So they took all their electronics and they potted it in silicone, so that way they could have it all untethered and on board, which is really nice. Alright, so that's enough about everybody else. Briefly going to talk about the stuff that I've been doing. So my work is on Bioinspired soft robotics. I've been working on an eel-inspired robot. So our inspiration is this leptocephalus. So baby eels, some baby eels are actually completely transparent when they're young. So you can see right through them. They wiggle in this undulating motion or williform motion. And so what we wanted to do was make a robot that could swim through the water silently, using very little power, blend into its environment, and not damage or scare off anything as it's swimming through. So we thought this would be a really good inspiration for our actuator. This is the way that we designed the actuator. So instead of using carbon grease or another like opaque material, we thought that if we're putting this into the ocean is conductive and grounded, so we could use that as one of our electrodes. And if we're using water as our outside electrode, what if we use it as our inside electrode as well? And so instead of using carbon grease, we're using water for both of our electrodes, which until this time, nobody had done this on a DEA for a swimming robot. Somebody else had done it for a pump, but nobody actually shown it on a robot. And so the way this works is we have 3 layers of the elastomer. We have 2 fluid pouches inside, and we have tubing that goes out to our electronics. Then as you apply voltage between one of the inside pouches and the outside water, the charges build up and compress the rubber, which causes it to bend. This is the way that we made it. So we took a strip of VHB, that tape, we put a mask down to control where we want the electrodes to be. So the VHB tape is very sticky, and we want it to not stick to itself where we want the electrodes to be. So we put a mask down, and we put some sort of passivating powder on top of it to keep it from sticking to itself. We found that cornstarch and superfine granulated sugar work really well. Cornstarch works well because it's very fine and it keeps it from sticking to itself. And then the granulated sugar works even better because it dissolves almost completely transparently and also dissolves very well. We tried salt, but in order to get enough coverage, you need a lot of salt. which doesn't completely dissolve, so then you come up with granules of salt in the actuator. So all of our actuators right now are full of sugar, so they're pretty sweet. So then we take the mask off, and then we put some tubing down and seal it, and we put another layer down, and then stack it all together so we can get this bimorph structure. We wanted to see how well it bent, so we put it on a frame in a little fish tank, and then we actuated it. And as we apply a voltage between the outside and the inside chamber, we can get it to bend. And we can do that for the other chamber as well to get it to bend the other way. So we measure how much it could bend either way, then we can compare that to some analytical model, because if we want to publish this, you have to have some sort of analytical model, just to show how much it bends for how much voltage you put into it. But we really want to make it swim, so we took it off the arm and then we actuated it at different frequencies. So the top video is at very low frequencies, or about 0.1 hertz. So at 0.1 hertz it bends and then stops, and then bends the other way and it stops. At very high frequencies, it bends faster, but it doesn't have enough time to actually fully get to the full amplitude, and so it doesn't move very quickly. At some Goldilocks frequency, it can bend almost all the way and bend quickly enough that it actually swims for the part more efficiently. We also tried it with manual timing, where we watched the actuators. That way we could actuate each side as it kind of came to its full motion. We got it to swim a little bit farther, a little bit faster. So this is about 9 millimeters per second. Some challenges with this design, though, is that it only swims, one, if there's some sort of rigid material at the tip. So I have a zip tie that's kind of biasing the direction of motion. And it's also only swimming when it kicks off the surface. So it's kind of like an inverted water strider. So it needs the pressure of the surface in order to get that kick to move forward. And so moving on, we decided to actually make several segments of these. So put several of these actuators in series. That way we can control the actuation and get it to swim by itself. I talked about safety. So even though we're using thousands of volts, since it's all encapsulated in a dielectric material, it's completely safe. So you can put your hand in the water if you want. It can also swim with other fish. These are some invertebrates that we found down at Birch. So we're collaborating with Scripps, and so they found these little invertebrates that will that we can put our actuator in with them. And they even at one point in the video, they're actually crawling on the actuator, so it doesn't seem to bother them at all. Then we also took it down to the Birch Aquarium and had it swim with some jellyfish and some other critters there too. What's neat about using water as electrodes is that it's completely transparent, or mostly transparent. So it's especially transparent with this light. I can't even see that it's there, but there's an actuator here over some multicolored rocks, and then it's here over some sand. You can kind of see some hazing where the actuator or where the electrodes are, but it's fairly transparent. And then we compared it to the transparency of an eel, how much light will actually transmit through the material. The eel is this green line, and then the actuator, the two different parts of the actuator, the hazy part and then the border part, are kind of bounded by how transparent the eel is. So it's roughly as transparent as an eel.
How would you find it again if you lose it in the water?
We use very small tanks and it's tethered, so that helps. You can always pull it back. So one of our collaborators works on fluorescent animals. He studies fluorescent fish down at Scripps, and he wanted to know if it's transparent, can we make it glow? And so we injected some fluorescent dye into it, and surely enough, it glows under a black light, which is pretty cool. There are eels in the wild that will glow under a black light. Under UV light, also under black light. And there's some debate as to why they do this. One of the popular reasons is that they use it to find each other during full moon spawning events. So the idea is that with this actuator, perhaps we could do it as well in terms of being able to localize it in the water. You could perhaps shine a black light on it and be able to find it, even though it's transparent to normal light. Here's video of it actuating under a black light. So this was before I had a good actuation sequence to it. So it's mostly just wiggling under a black light, but baby steps. Okay. So then, like I said earlier, in order to get it to swim forward, we put 3 of these actuators in series, and then we suspended them from their tubing. We're going to put it on this swinging arm, so that way we can control the depth of it as it swims through a tank. And then we actuated each of the panels in a sequence to get it to do this kind of undulating motion. So in the top right video we have, so the screen inset is which ones are on, which ones are off. So in this first one, the front left and then the back right are on, so it bends down. And then we just control that sequence to get that ripple to try to go through the body.
So let's say that a real ill does the same thing. Is it like your ratio of your actuator to real ill? Is it like 1,000 to 1 or something like that?
A ratio of how many actuators
The
versus?
ill has versus yours.
Oh wow, yeah. So we have 6, and in terms of like discrete muscles in an eel, I have no idea. I mean, it's thousands, I would say. Yeah,
So that's how they get their smoother and stuff like that.
absolutely. Yeah, because this is highly discretized, right? Because we only have 6, but then theirs is, it's much more of a continuum of actuation. Yeah, that's a very good point. So here's a video of it swimming. Eventually. So the first video is of it swimming under normal light. There we go. I did speed it up 2 times because it was a little bit slow and boring for some people. But yeah, so this is it swimming under normal light. I'm still working on the actuation sequence, so it's a little choppy, right? And I think it had to do with, I was using a MATLAB code to run the Arduino, and I feel like there was some sort of pause at the end of each segment, and so that's why it's actuating and then stopping. But still working on figuring that out. So that was under normal light, and this is how it looks under black light or party mode. What's interesting is like in the paper that we wrote about this, like we focused very little on the fluorescence. It was mostly just kind of an afterthought. But all of the news, all the press releases, like this is the image that everybody wants to see. They want the fluorescence, they want the pretty pictures. Even though arguably it has very little functional significance, it's art, I guess, and so it was very much more captivating. So that was an interesting lesson in journalism. Okay, so that's all I have for that. Thank you for your attention. What questions do you guys have for me?
Why was Jellyfish hard to replicate?
Yeah. It's hard to say. So it goes back a lot to the amount of pressure that these can generate. And so one of the constraints that I'm putting on myself is that I want these bodies to be completely soft. So I'm avoiding any pre-stretch. So when you pre-stretch it, you have to stick it to something that's rigid to hold that pre-stretch. And so that's what a lot of other groups are doing. But then you have something that's rigid, and that's hard to say that it's a soft robot at that point. And so since we're in a soft robotics lab, I want something that's completely soft. And so I can't get away with pre-stretching the rubber ahead of time. And so I get less force and also less actuation frequency. And so I can't push the water as hard or as quickly as it would take to get easy motion as a jellyfish. But I've gotten a little bit of motion. I can get wiggles, but trying to generate productive wiggles, and it's challenging to do both. Yeah.
So I can see how something like this would be applicable for like physical therapy, for example, because it could give patients a more normal range of motion other than your actuators. So I was wondering, what other kinds of fields do you want to see soft robotics applied to?
Great question. Yeah, so in our lab, we have a lot of focus on underwater robotics, and a lot of that's due to we have a lot of funding from the ONR, so just kind of the way that worked out. But we are also looking at, we're collaborating with the medical school to make a surgical device that you can control how stiff it is. So for one of the surgery, for some surgeries, you have, like in your abdomen, you have to get certain organs out of the way. And so for one example, they have a liver retractor. So if your liver is in the way during surgery, they have a strip of steel that's somewhat malleable, and so the surgeon will bend it into shape and then shove it into your abdomen, and that will hold your liver out of the way. But if you want to do that through minimally invasive surgery, it's hard to get that big strip of steel through that, and they've had complications with it. And so what we're working on instead is a compliant strip that has, basically think of like a balloon that's thin and flat, and then it has how about bits of sandpaper along it, and as you, if you have air inside the balloon, you can kind of move things around easily, but then if you suck all the air out, it gets very stiff. And so we're doing something very similar to that. So it's very easy to bend, and it can go through a very small hole. So you can insert it into the body in a very small, through laparoscopic surgery, and then the doctor can bend it into shape and then pull the air out of the balloon, and it'll hold the liver out of the way. So we have some interest in like medical robotics. Other questions?
This control signal that you've worked on to get the right sequence and the right timing, is it open loop control? There's no
Yeah.
feedback mechanism?
There's no feedback right now.
Would there be benefits? Can it benefit from detecting its own speed or motion to adaptively get a better motion?
Absolutely. Yeah. So in one of the earlier videos, I was showing where we had like this just applying a fixed frequency and getting a certain actuation. But when I took control over it, when I actuated one and then the other one, once it had gone through its full range of motion, I got much better performance. And so if we had some maybe accelerometers at different bases of the structure, that could tell when it's achieved its full range of motion, or at 90% of its range of motion, and in order to tell it to go and actuate the next muscle in the sequence, that would be very helpful. I just haven't done that yet.
Would that pretty much be limited by how much electronics can be on the device?
That's what I would say so, because so anything's going to weigh it down. And we can use ballasting, we can add air to offset the weight of whatever accelerometers that we put on it or other sensors, but we would need to be able to waterproof them and also not impede the actuation. These are again very soft and flimsy, so it's very easy to weigh something down and won't stick in it. But there could also be vision approaches as well. So if you have if we could get away with off-board vision and use that for our feedback loop, that could be really helpful.
You're saying cameras, external.
Right.
So the way it is right now, the control signal's coming from a computer that's off-board, right? And then it's tethered in.
Yeah. But we're looking at making it untethered. But I mean,
How would you do that for the power though? You're talking about thousands of volts, right?
so thousands of volts, but actually very low power. So
low current.
Yep. So we have there's XP Power. They make these little.
Coin cell? Like
they're-
coin cell batteries?
So yeah, you would use a coin cell battery that would go and power apply the voltage to this transformer. So you can get these transformers that will take 5 volts in and ramp it up to 10,000 volts out at half a watt.
But how big is the transformer?
Oh, sorry. So the transformer, it's a little bit smaller than a square inch, or a cubic inch. So that's the 10,000 volt one. If you can get away with 5,000 volts, it's how about 4 quarters stacked on top of each other?
Mm-hmm.
You can use that for your rigid surface even in the front.
Yeah, exactly. Yeah. Or the manta ray one, they just had a kind of like a tube of the robot. Anything else?
Since you guys do a lot of things in the water, do you do anything with the robot sub teams in town?
No, we haven't yet. Yeah, they're a little bit larger scale than we are. All of ours is pretty small stuff. Not nano stuff, that's pretty small.
You mentioned that there was a group that had done a multi-layer version of that. How much work is going on in that area, like to be able to either lower the voltage or increase the force that can be applied and so on?
Yeah, there's several groups that are working on that. Harvard's one of the big ones right now. But there's a few different groups that are doing it. And also the company that had the Blimp, they are also working on a small scale actuator that uses these multiple layers. The challenge with multiple layers is that it's hard to get consistent thicknesses without defects between each of the layers. So the one that I showed you, the Quadrants, I think they have maybe 8 layers. The fish, I believe they're on the order of 4 to 8 layers. But when I was talking to him at the conference, he said that many of them fail. So they go through a whole lot of failed ones because it's really hard to get high quality control of these devices. The company over in Germany, they've made ones that are, say, this thick or this tall. So on the order of maybe 100 layers, and they've found a way of automating this process to make really nice, clean, reliable actuators. But that's German engineering for you, I suppose. We don't have that capability in our lab right now.
Did they 3D print it or what?
No, it's a layer by layer process. So say you have a liquid rubber that will cure under an ultraviolet light. So we'll go from a liquid to a rubber under ultraviolet light. So they'll take a spinning disc, they'll pour the rubber on it, they'll spin it really fast to get a thin, uniform layer of it, and then they'll pattern on their electrodes. So they can use something like what you would use for microfabrication, like for making chips. You can apply carbon nanotubes through masks to delineate where your actuators are. And then they would spin another layer on top of that, and then cure that under a black light, and then electrodes. And they just keep repeating that process, and then they have a stamp that will cut out each of their stacks, and then they assemble those into actuators. But yeah, getting 100 layers without defects is really impressive. Especially because Harvard can do, 4 to 8. So. Other questions? Alright, if not, let's close. I'll stick around for a few minutes if you guys want to talk to me one-on-one. I also have cards if you want my email address. We can talk about it afterwards as well. But thank you all for coming. I really appreciate it.